All right, good afternoon, and welcome to the 2023 Albrecht Lecture. My name is Pat Markey. I'm the director of the School of Natural Resources. It's lovely to see such a full room today. I'm going to give you a brief introduction about the Albrecht Lecture, and then I'm going to turn things over to Dr. Morgan to introduce our speaker. Dr. William Albrecht was a soil microbiologist in the Department of Soils at the University of Missouri from 1919 to 1958. He was department chair from 1938 to 58 and also a president of the Soil Science Society of America in 1938. He was internationally recognized for pioneering work in soil organic matter properties, nitrogen fixation, and his progressive insight on the relationships of soil status to animal and human nutrition and health. He recognized the importance of calcium as a nutrient in plant growth and health, not limited to use as a soil amendment to adjust acidity. Dr. Albrecht also developed many biological assays that are precursors to today's soil health indicator measurements. He investigated soil management practices to maintain, improve, and restore soil organic matter, practices that were based on studies at Sanborn Field, the longest continuously cultivated agricultural research site in the United States. I think everybody in the room knows it's about a block that way. If you didn't, now you do. We're grateful for the generosity of the late Dr. Carl Ferguson, whose gift in honor of Professor Albrecht allows Mizzou to celebrate Dr. Albrecht's legacy during our annual Earth Day lecture. Anne Perret is the granddaughter of William A. Albrecht. We don't believe she's with us today, but we extend a thank you and a special welcome to her. So now, to introduce our guest speaker, I'll turn it over to Dr. Morgan Davis, SNR Assistant Professor of Soil Science.
All right, thank you, Director Market. So it is my privilege to host the Albrecht Earth Day lecture each year, and a role that our speaker today knows well because he did that formally. So we are privileged today to have Dr. Robert Kramer deliver the Albrecht Earth Day lecture. Dr. Kramer is an alum of Mizzou, completing both bachelor's and master's degrees here. He then went on to a PhD at Mississippi State. He currently serves as adjunct professor of soil microbiology in both the School of Natural Resources and the Division of Plant Science and Technology. And over the past 40 years has helped us frequently teach environmental soil microbiology and co-teach advanced weed science. Dr. Kramer retired after a 32-year career as a microbiologist with the USDA Agricultural Research Service and had projects that included biological controls of weeds, pesticide fates in the environment, soil microbe, plant pesticide interaction, and other soil health assessments, and was really a precursor, doing a lot of this precursor research of soil health for a long time. So he has co-authored 2 books, 30 book chapters, and authored or co-authored 170 refereed research articles, and is I will also say, a genuine mentor and has been a critical piece to our soil science group and curriculum over the years, and definitely thank you for that. So today, Dr. Kramer's talk is From Albrecht to the 21st Century, Missouri's Legacy of Achievements in Soil Biology and Contributions to Soil Health. And with that, I will turn things over.
Thanks, Morgan and Pat, for those nice introductions. I guess coming full circle does make me an official member of the senior faculty now, because retirement is not really retirement, as a lot of people know. So today I'd like to start off and kind of give you a little bit of where I'm from. This is our farm in Osage County. A lot of hills, cows. Down there is our farmstead. If you see the big barn there, that's what it looked like in the 60s. So what I'm trying to show you is that really come from a small farm background, 225 acres that my dad there made a living on. He's a true American farmer, never had an outside job, made a living on that farm back in the 50s, 60s, 70s. We're fifth generation, or I am, me and my brother here, farmers. Our grandfather bought this place in the early about 1920. I think that's so we claimed to be a Missouri Century farm. So, and my mother there, she passed away about 15 months ago, but her full-time job was raising 7 kids. So it was one of these farms that we really don't see much anymore. We raised maybe about 12, 13 crops, not all in the same year, but we rotated them through. Had a lot of frost-seeded clovers and things, and the wheat and the oats before we knew what cover crops were called cover crops. So, so I just want to, a lot of that has rubbed off on us. One of the things that my dad said that he really enjoyed, the most that he really enjoyed about the farm was that he liked to raise corn, as we can see here, and it really made a big change for him when they introduced the hybrids, Missouri 17, which was developed here on campus. Really got them transitioning from open pollinated corn, and started to see the performance and the yield increases when these hybrids were released. And that kind of brings us into what we want to talk about today, is what achievements have been made here at Missouri, specifically in soil biology. And a lot of it has its roots in research, or at least observations that was done at Sanborn Field that we see here. This is kind of a timeline that I have that coincides with the development of soil microbiology, soil biology. And note that Sanborn kind of coincides because about 1888 was when a lot of the discoveries in soil microbiology was going on, with discovery of nitrogen fixation in rhizobia, mycorrhizing, things like that. So it's a relatively young discipline. I remember not long ago when I was teaching some soil microbiology classes here, I would say, yeah, it's only been 100 years ago, but that kind of dates me because that was 1888 and all that. But anyway, as we've mentioned, Albrecht, 1916, took the position here as a soil microbiologist, and there's many other things going on. The antibiotics, which we'll talk about in a little bit. Later on, soil health, soil quality development, and then now we're into the molecular age with most of the areas that we study in agriculture. So we already know about Dr. Albrecht. Dr. Mark had already mentioned about all his achievements professionally. He also was in charge of legume inoculation development for providing those inoculants for farmers. He made most of these cultures, grew these cultures in the basement of Mumford Hall, prepared the inoculant in these bottles, and then they were given out to the farmers. The way the Extension Service worked at that time, the farmers received these products to use on the farm. So he was very much into organic matter, studied early days of soil organic matter research, had a very good article in the Yearbook of Agriculture of 1938, Soils and Men. And as has already been mentioned, he recognized the importance of calcium as a nutrient, in addition to it being a soil pH amendment. Demonstrated, this is one of his more controversial achievements, was that he believed that proper nutrient proportions based on a balanced base saturation and sufficient micronutrients results in optimum plant growth and yield performance. He showed how to do that. And then also, he was one of the early people to recognize what we now call soil health, because he visualized that in order to have good plant health and supporting animal health and even human health, you got to have a healthy soil. And we're still pursuing that and looking at that particular topic. One of the Missouri Agricultural Bulletins that was produced with after his retirement, when they were doing all the events for him, a chapter written by a medical doctor, Pottinger, really showed that his perspective of connecting soil productivity to animal and human health was very important, because it meant that he was not interested in just quantity of yield. That's how we think now with commodity crops. There's always yield contrast. More is better. But he realized that, it's not the bushels per acre, it's the nutritive value. And we'll talk about this a little bit later, about what is the nutrient density of some of the foods that we have available now. And he would use protein content as an index of quality. And we are aware of his use of biological assays. He used rats and even cats, and then later on he was getting into some of the livestock. But he realized that in order to see how effective some of these management practices were, is to see how these animals performed on what was harvested off these fields. And also, he provided soil from Sanborn Plot 23 for the isolation of the microorganism producing the antibiotic aureomycin. That kind of gives me a little leeway into the next part of this talk, is to give a little bit of a history lesson on the discovery of aureomycin. So let's go back a little ways. 1928, the first antibiotic was discovered, which was penicillin in the United Kingdom by Alexander Fleming. Now, he did not file a patent, and it was felt that it should be available for all who wanted to use it. So this is pretty important. That antibiotic was not patented. And then in 1941, his cohorts, Flory and Chain, actually smuggled the penicillin-producing microorganisms to the United States, because it was during World War II. They got it through the Nazi blockade. The U.S. government invested in the mass production of penicillin for the war effort, because they realized that this was a very valuable pharmaceutical to have. So it's not known whether they contracted it out to some of the pharmaceutical companies at the time, but Pfizer was one of the companies that really took command for mass production, and then followed up by producing it for domestic use after the war. In the 40s then, because of the success of penicillin, there was a considerable effort among competing pharmaceutical companies to develop these highly effective antibiotics so they would have something to market. So in 1943, streptomycin was isolated from a bacterium by Selman Waksman, who we have here at Rutgers University. Selman Waksman was one of the premier soil microbiologists at the time. He was very efficient, ambitious, motivated, and he had a very large lab that he dedicated a part of it just for screening purposes for antibiotics. So they finally found an effective one, streptomycin. It was claimed to cure tuberculosis. That was the big selling point, and he traveled the world promoting his antibiotic. Now, then it was patented in 1948 with exclusive rights to Merck. Now, it took a while to get patented, because at that time the government thought that anything that was a natural product was not patentable. But he was able to convince them that, it really wasn't out of the soil, it just came from this organism, so it's not a natural product. And he was pretty shrewd about that, so he finally got it patented, and it was exclusive rights to Merck. So Merck had an antibiotic. So by 1945, these other companies, Upjohn, American Cyanamid, they're still looking for sources of antibiotics. So this Dr. Benjamin Duggar of Lederle, which is a subsidiary of American Cyanamid, requested soil samples to screen for antibiotic-producing microorganisms. So he contacted Dr. Albrecht, who collected the sample from Plot 23 out here, a continuous Timothy plot. And there was a connection between him and Duggar, because Duggar was at one time a faculty member here at the university in the early 1900s, so he had a connection. He was later a on the faculty of Washington University in St. Louis. And he was working, then he retired and he was working for Lederle in his retirement. By 1948, they isolated Streptomyces aureofaciens, which is an actinomycete that produced aureomycin. It was a tetracycline type antibiotic and was very effective on many infectious diseases, enteritis, rickettsia also, such as Rocky Mountain spotted fever, that kind of thing. So it was very effective, and it didn't, and as you can see, it didn't take long for it to be patented. It didn't take as long as streptomycin. So by 45, Fleming and his colleagues won the Nobel Prize for the penicillin discovery. By 1952, Waxman won the Nobel Prize in physiology or medicine for his discovery of streptomycin, the only soils person that's ever received a Nobel Prize. I've got 1953, it should be 1958, Plot 23, a part of the soil from Plot 23 became part of the Smithsonian Institute exhibit that was entitled Antibiotics, the Wonder Drugs. This is Plot 23 here, and this is the other Plot 22 of Timothy on Sanborn. You can see it's a little bit poor. Not a whole lot of Timothy there. In fact, at the time, one of the deans said, "Oh, there's so much weeds and broom sedge growing on Plot 23." He told Albrecht, "You need to be doing something about that because it doesn't look good." But apparently, for that organism to grow in there, it might have been stressed enough that it was producing enough antibiotics. Nobody knows because nobody followed up on the study. In contrast, Waxman's streptomycin organism was supposedly isolated from a very fertile soil. So you can see it's a lot of serendipity in this isolation business, and it's hard to say, make a hypothesis on that. So this is Duggar. He was the one that's responsible for isolating the organism that gave us aureomycin. I've already mentioned that he was at Missouri early in the 1900s. He was a mycologist in the Department of Botany, and he was a researcher with American Cyanamid, our Lederle labs. They produced a symposium and published it in the New York Annals, the Annals of the New York Academy of Sciences. Many people who had tested the drug on several different pathogens had papers on it, reported the effectiveness of aureomycin on numerous gram-negative and gram-positive, those are bacterial, infectious bacteria, and it became a very profitable antibiotic for Lederle. These are some of the shots. These plates are all cleared out. These spots are the organism that's producing the aureomycin. As you can see here, here is streptomycin. It just has some clearing zones against this particular pathogen here. Aureomycin pretty well clears out the entire plate, so it was a very effective antibiotic. Okay, so this is a tetracycline type antibiotic. One of the things about aureomycin that was discovered was that it became a very good antibiotic for livestock growth promotion. They were feeding subtherapeutic doses to chickens, resulted in more than 50% weight gain than normal. And this fellow Jukes was the one that got so excited about it that he just kept testing livestock with the antibiotic. And one of the things that then happened is that it led to routine addition of antibiotics to feed chickens, cattle, hogs. As you can see here is an example of a feed sack that is laced with aureomycin specifically for livestock. So in 1955, 500,000 pounds of this antibiotic provided livestock feed in the U.S. By 2001, it was 24.5 million pounds for livestock use. And so what happens? You're using so much of this, we really got to see a lot of antibiotic resistance develop in bacteria, and many of these antibiotics, especially the tetracyclines, became ineffective for controlling human infections because you would be exposed to these bacteria that had antibiotic resistant genes in it, transfers that into your gut microbiota become antibiotic resistant, and it's a real problem because then you have to search for others. So by 2000, the FDA ruled that the antibiotics for livestock use must now be prescribed by veterinarians, and use of growth promoters are mostly banned by 2017, but I'm not sure if that's a complete fact or not. All right, so tetracycline, you can see why it's called tetracycline, 4 rings in the structure. This is streptomycin, as you can see, is different. Here's a sample of soil that was sent to the Smithsonian. So the current human use for aureomycin, it's very good on dermatology conditions like acne and topical use to treat those diseases. We mentioned the rickettsia diseases. It's still very effective on Rocky Mountain spotted fever infections, and for some reason Lyme disease as well, because that pathogen, the pathogens for either of those 2 diseases have not developed antibiotic resistance. The global market for tetracyclines in 2021 was about $8 billion. So it's still making quite a bit of money I'm not sure who's producing that now. I guess it's still American Cyanogen or Upjohn. Zoetis produces aureomycin for their veterinarian products. Oh, what happened? Okay. All right, so those of you, I guess there's a few of you here that have had my class in soil microbiology. There's a plaque out on Sanborn Field that says aureomycin originated here. And the first word that says, the fungus, Streptomyces aureofaciens, was isolated from plot 23. So this is one that I always have give to the class and say, what's wrong with this plaque? It's not a fungus, it's a bacterium. And, you know, here it is out in the open. Of course, average citizen wouldn't know the difference, of course, but it's just a sticking point with me. And why did this happen? Well, it's an unusual bacterium. It does produce threads or filaments like a fungus if you look at it under a microscope. And Waxman knew that these were actinomycetes back in the early 1900s. But I think Duggar, because he was a mycologist, decided that it was a fungus. And even many articles today, I have a book that's called Big Chicken that is based on how chickens have been fed antibiotics over the years and what the problems are. Even in that book, published in 2017, still refers to it as a fungus. So they use it interchangeably as a source of the antibiotic. But it's something that probably should be revised or updated on the Sanborn plaque. This is a fungus. It's all segmented and everything under the microscope. This is the actinobacterium, very thread-like. I know it's hard to distinguish, but there is a difference. Okay? All right, so that completes my little thing on aureomycin. It's the 75th anniversary of its discovery, I believe, or patenting. I'd like to say that I have a connection with Albrecht. This was my advisor here, George Wagner. But George's advisor was George Smith, not the George Smith Nobel winner here, but George Smith that was hired in 1937 as a fertilizer person in soil science. In fact, he used to teach a course called fertilizers, and you learn all about where they came from and what they're made of and what they do. It was a very good course. But Albrecht worked with both of these guys, and so I can't claim any connection to him. But what I did find, and I know this is not any self-promotion, but I am a academic great-great-grandson of Waxman. And how I found that out, And how I found that out was that I was looking in a book reading about Waxman's work, and there was this picture, and I looked at it and I said, well, that looks like Lloyd Frederick. And Lloyd Frederick was a microbiologist at Iowa State. He was a mentor of my advisor at Mississippi State. And so trace that back, Frederick, whose mentor was Starkey, who was an associate of Waxman, who mentored him. So there you go, the academic genealogy lesson for the day. Okay, so getting back to soil biology now, Wagner did a lot of work out on Sanborn Field, or he had students that did that. Even though he did not have a soil microbiology degree, the fact that he succeeded Albrecht, I think because he did a lot of nitrogen transformation work with George Smith. So he had a long career here, 57 to 92. He chaired agronomy for a year or so, fellow in the societies. He, along with his associate here, Grigory Boyanovsky, who was an immigrant from Ukraine, did a lot of work with him, teamed with Wagner to accomplish a lot of significant research projects. And these are some, his greatest achievements were in the area of carbon cycling and carbon transformations. But George Wagner had aspirations in many areas, and I'm not going to go through all of these, but things like nitrogen fixation, rhizobium, and even some pesticide degradation, and aflatoxin production, and things like that were, and he was very meticulous. Every publication he had was spot on. It was written the right way. Here's an old picture from some newsletter where he's out on Sanborn sampling, probably taking carbon dioxide samples. I remember that he would put a tent out here over part of a plot and then pump it full of C14 labeled carbon dioxide and then label these plant parts and take those tissues to see what the partitioning was. Probably couldn't do that today, that kind of thing. Also collected a lot of carbon dioxide out of the soil using these indicator tubes. He was quite a pioneer in this area. He looked at C13 and demonstrated, where the stable soil organic matter origins were. He determined that the sequestered organic matter out here at Sanborn was the same as that at Tucker Prairie, which is some, 10 or so miles east of here down Interstate 70, which indicates that, yes, this was all prairie at one time, contributed to the organic matter that is under Sanborn Field. Did a lot of meticulous work such as this. This is an chronoisoplethograph, which basically means he tracked CO2 at depth in the soil under different plants, different crops, and detected their depths and showed how the variation in carbon dioxide in the soil under these different crops at different times of the year. This was all done before we had a lot of more elegant type of instrumentation that we do now today. Soil enzyme studies, being from my lineage, including Iowa State, I learned a lot about soil enzymes before it was very popular. We did soil enzymes in Mississippi State. So I brought that back here. I think I probably did the first enzyme survey on Sanborn Field on certain plots. And I also introduced it into the soil microbiology class when George was on sabbatical in 1986. So now it's become a very popular tool to do these assays in relative to soil health and other parts of disciplines within soil microbiology. Anybody that's done enzyme work can recognize the name Ivasi because she was a student of Tabatabai at Iowa State, but she's now at Lincoln University. She did soil enzyme analysis on 15 of the long-term cropping systems out here and showed that there's a strong relationship that exists between enzyme activities and management practices. And she had, in this paper in 2003, she predicted that these have potential to be used as indicators of soil quality and sustainability. And we're still doing soil enzyme studies. Some of my colleagues, Ranjith, Chung Ho Lin, Kristen, Tim, still using a lot of the enzyme studies, even though that I agree with Jordan that they do have their limitations. They are good indicators of microbial activity and the relationship with soil, what we now call soil health. Diane Jordan was here from 91 to 2000. I convinced her to use soil enzymes, and we did a study on Sanborn. I believe it was probably the first soil quality research out there, looking at bioindicators of soil quality and long-term cropping systems. She also did work with earthworms and phosphorus-solubilizing bacteria and mycorrhizae. This is our paper. We looked at microbial carbon, phospholipid fatty acids, fungal and bacterial biomass, soil enzymes as microbial indicators of soil quality, and found obviously Sanborn is a very good proving ground because they have these contrasting management systems, and of course we could see these differences using these techniques. So later on we continued with the soil health has become soil quality, and soil health became more popular. This is a study that Kristen Veum headed. She was postdoc in my lab at the time, looking at indicators of soil quality over an agricultural management continuum. It included Sanborn plots, and basically what it shows is these are soil health index scores, or soil quality index scores, and basically anything that was perennial or was in rotation and had manure as fertility graded out high with soil health, indicating those practices promoted soil health, as opposed to management systems that were continuous monoculture without any cover crops scored very low. And these, one of the things that came out of this paper is that we did use soil enzymes, and again showed that they were potential predictors of soil organic matter dynamics. We also included spectral analysis here for potential for estimating carbon and nitrogen fractions, as well as soil enzymatic activity, which is moving on. If we can, with Ken Sudduth and his team, along with Kristen, can develop these sensors, it'll make soil health assessment a lot more efficient rather than having to pull samples throughout the field. So Kristen also developed what we call a continuum of soil health, which is the linkage of microbial function and indicators across a continuum of vegetation and land management. So higher scores with these more perennial systems, organic amendments, even with livestock in the mix. Restored prairies are much higher, and then we go down this continuum graded lower with the monoculture annual cropping systems. Obviously, if cover crops are included, that gives it a more improved soil health, but if it's continuous, say continuous corn, nothing growing in the winter, in the off season, these scores are very low and indicates very low soil health. Randy Miles did a study where he looked at several plots on Sanborn for active carbon. Active carbon is a labile carbon that is very much available to the soil microorganisms that helps them keep their activity up, maintain their function, and which is growth promotive to the plants that are growing there. And so what he saw, as you would expect, rotations have higher active carbon. Here is plot 17 has never been fertilized continuous corn, very low active carbon. These plots here should be continuous Timothy, very high active carbon because due to the continuous inputs of organic matter. And then you get this segregation of the fractions of the different soil organic matter that really helps feed those microbes and promote their function. So the last study that I show from Sanborn, again with Randy Miles, graduate students, Saranya, shows the soil health assessed on selected management systems, and again we see very similar trends. The prairie plot, Tucker Prairie, continuous Timothy, very high scores. And this was used with a different assessment compared to what was used in the previous study. Aggregate stability, bulk density, active carbon fraction, these are all soil health indicators that are plugged into this model to come up with these scores. So again, a very kind of proof of concept. We've got those management systems. We can do soil health analysis on it. It kind of helps us to figure what we might expect when we go on farm, knowing the management history when we go and take those assessment samples. All right, so soil quality, soil health, a lot of people like to keep these interchanged, but to me, soil quality, which was developed several years ago, back in the 80s, it was really, first of all, it is the functional capacity of the soil to meet certain needs, and at that time, optimum economic production of the crop was the emphasis. Soil health involves more of a vital living system. We're more into sustaining biological productivity along with production, but we do have that emphasis of including biological indicators. So I just show this kind of make it clear. Some may not agree with, but as I might say, I have opinions and they reflect me and not everybody else, not the college, not the school. So keep that in mind too. All right, so the outcome of all this soil quality, soil health projects at Missouri led to the evolution of the soil health assessment here. And I'd like to go just briefly through some of that history. About 2011, David Hammer and myself, we started discussions to develop a soil health lab within the old soil characterization lab. We already have a good lab covered by the soil and plant testing lab for the chemistry component, but we needed to, if we were going to do this properly, we needed to expand to include physical and biological components that are parts of the soil health assessment. So we developed a working group, and I apologize if I'm missing somebody here, but Hammer, myself, Miles, we had some NRCS people, Jorge, Mark Abney, we had Kristen, Carrie Clark, Donna Brandt, Russ, Tim, and Lauren Cotright, who is also NRCS. And I also like to say that Ann Kennedy, who was USDA ARS soil scientist at Washington State, was very helpful because I had been consulting with her many years on the phospholipid fatty acid analysis for microbial components, and she had that system down, so she served as a good consultant. I've sent at least 2 or 3 students out there to train with her at the time. And so that's why we decided to use that as our soil microbial component analytical or analysis rather than something like genomics, because at the time the genomics core at MU I don't think had been established yet. And in order to do that analysis, it would have been very expensive. So that's one of the reasons why we're with the PLFA. So we secured the funding. We began setting up the lab, I think 2013, including the PLFA analyzer. And then we kicked this off. We had a series of soil health workshops and training sessions with NRCS because they were the ones that wanted to get this soil health incentive going with farmers. We had a Natural Resources Conference Soil Health Symposium in 2013. We had a series of soil health workshops for farmers and users and other extension people at several key locations around Missouri. And Kerry Clark and Kristen took a big lead on that just to get that underway. Soil health expos were held from 2013 to very recently. A lot of them were at Bradford Farm. And then about 2014, the NRCS Cover Crops Economics tool came out because that was a very important practice in order to use to improve soil health. We were also involved in the Sheraton County NRCS Soil Health Demonstration Farm collaboration that I think went from 2012 to 2020. And then finally, the Soil Health Assessment Center was relocated to where it is now at South Farm. As you can see here, I think you need a new sign, Donna, but it's getting a little faded. But anyway, there it is. We also are blessed to have some soil health collaborators. We do a lot of work through, or I have through the Center for Agroforestry. Now you have the Center for Regenerative Agriculture. I know that these are meshing very well, plus NRCS, DNR, and I'm sure I'm missing maybe MDC, but soil health has really caught on. And I think a lot of it has to do with many of us that are in this room that have done some of the foundational work on soil health previously, whether it was on Sanborn or Farmers Field or at Centralia at the plots there, the USDA plots. Okay, so I want to show, I've got a little time left, what the projects that we've been able to do based on these foundational research. I'm only going to show two because I don't have time to show everything. A lot of soil health status on native prairie and reconstructed prairie ecosystems. This is one established prairie plants on a restored prairie at Prairie Birthday Farm in Clay County. This was established on a very eroded slope of Sharpsburg silt loam in the Missouri River hills. There's hardly any topsoil left, about 2 inches. I think this was started in the mid to late 90s. This is 2006. You see how the establishment went and it was established with no herbicides, no tillage, but it was burning, grazing intensively to kill off the old fescue stand to get these plants established. And as you can see we could increase the organic matter from 2 to about 5 to 6% over a span of 20 to 25 years, and mainly due to the deep rooting into the soil. We didn't necessarily add any to the topsoil itself because that's pretty hard to do, is to generate new soil, but the fact that we generated new organic matter helped keep that soil in place, and it's permanent. There's no need to try to produce something on slopes that are about 10%, 5 to 10% on that landscape. At that same location, a little agroforestry, which is actually fruit trees in an orchard with understory of native plants, forbs, and grasses. They were able to, since converting that orchard to native vegetation, soil organic carbon has increased by about 50%. This just shows you the increase in microbial abundance with the organic orchard and alley, and there was some with biochar compared to a nearby site that was cultivated. I show a picture of mycorrhizae on the roots of these trees and plants because that was one component that was increased quite a bit due to this particular management. Sticking with the agroforestry theme, this is pecan planting in Sheraton County. And the unusual aspect of this is that the alleys are planted to a perennial clover called Kura clover that did very well there. A lot of people told that farmer, said it won't work because they're too far south, but it established very well. And we did looked at that. It improves soil quality considerably, also suppressed weeds, and it serves as a source of forage, hay, even seed, while these pecan trees were maturing before they produced a nut crop. And again, we can increase soil organic matter over time compared to a nearby tilled crop that organic matter never got over 1.5%, whereas with Cura, that he was maintaining organic matter over 4%. Fescue was pretty stable at 3%. So again, another soil health assessment of a practice that shows that these soils are very much improving over time in those hilly Missouri River loess hills. Okay, so now just to change it a little bit, not getting away from soil health, but getting into another aspect of soil health is, if we follow up using Albrecht's nutrient balance concept for improving crop growth and grain quality and soil health. This is from a recent study by Tim Reinbach, where he used Albrecht's recommendations to fertilize this particular corn plot. And what he showed was, with using that, crude protein increased, as did calcium, and these two essential amino acids, lysines and methionine, just by balancing the nutrients in the soil. Also, I didn't have the graph, but grain yield increase and soil health indicators were higher with Albrecht's recommendation. And then he also had a treatment where he included cover crops, and that boosted the grain quality components even higher. So what we as soil professionals, should we be concerned with food or grain quality and ultimately with human health? I think we've done a great job figuring out how to improve soil health from the standpoint of productivity, many of the other edaphic factors, and ecosystem services. But when we look at it from a soil health, many of the definitions we see with soil health, regenerative agriculture show that we're supporting human health, we're maintaining the health of people. Even the practical farmers of Iowa saw an Iowa with healthy soil, healthy food, and all this is needed for resilient and vibrant communities. So is there a mandate here to be relating soil health to human health, and how do we do that? And these are just my opinions, so nothing that I'm trying to sell you at all. So there is concerns about quality of food produced. Farmers, you read some magazines, Successful Farming, No-Till Farmer, there's usually farmers in there that are beginning to question, is the goal of high yields as important as the nutrient density of the harvested grain that I'm producing? From an industrial agriculture mindset, we often think grain as a commodity, not a food. Thus, we go for maximum production, regardless of what the grain quality is. So the old adage of feed the world is kind of outdated. I like what Bob Quinn says in Grain by Grain. We need to nourish the world, because sometimes what we are producing may not be as healthy as we would anticipate. But if soil health is to be linked to human health, extraordinary evidence will be required. Soil health that improve food quality need to be validated. We can actually begin to solve the human health crisis. What's the biggest contributor to the soil human health crisis is diet. Our kids are eating ultra-processed foods. They're eating Wonder Bread that's stripped of everything, including fiber. So these poor diets and are responsible for most of the non-communicable diseases that could be prevented with diets of real food. Not with high fructose corn syrup, not with low or no fiber processed foods. So maybe we're extending ourselves too far, but these are just food for thought. But it's going to require collaboration with nutritionists and dietitians to evaluate the improved food quality, produced under healthy soil in diets if we're going to see that this relation is true. So, I can give you an analogy, but let's look at the rhizosphere of a plant and the human gut. In the human gut, fiber is very important. There's soluble fiber and there's insoluble fiber. The soluble fiber will feed these microbes that are in your gut and keep them going. The insoluble fiber is slowly digested by some of these components, and it releases the anti-inflammatory compounds that is needed to ward off diseases. That keeps you healthy. It also helps with the mucus layer on the inside the intestine here where the good microbes are. And if you see here, the main component that helps this is diet and the microbe interactions. 90% of us are microorganisms. So that diet is important, and when we eat foods with no fiber that are loaded with sugars and salt, we are get an imbalance in here, and a lot of the inflammations, a lot of the liver diseases, because a lot of this, say, fructose goes to liver. If it can't be metabolized, and becomes non-alcoholic liver fatty liver disease. So something to think about. In the rhizosphere, my similar compounds would be organic carbon, labile, and complex carbon. The labile carbon, the active carbon that we're talking about, helps feed these rhizosphere microorganisms, and it protects the plant. It protects the plant, and it provides growth regulators for the plant, or growth hormones. The complex carbon helps the organic matter, build organic matter. And the biggest factor here are edaphic factors and the microbe-microbe interaction. Sounds very similar to what's going on in the gut. So, feed the gut, protect the liver, diet of non-processed foods, fiber-containing foods. Feed the rhizosphere microbiome, protect and nourish the plant, protect soil integrity, reduce tillage, reduce synthetic chemical inputs, productive crop varieties and cultivars. So you've probably heard about Montgomery's paper where they were comparing what he called conventional and regenerative crop systems. It's a very broad survey across the country, but what they found was that with regenerative, increased soil organic matter, the soil health index increased, and they found that soil health influences phytochemical levels in the crops. These are your antioxidant compounds and vitamins, indicating that regenerative farming system may enhance dietary levels of compounds known to reduce risk of various chronic diseases. But again, that was a very broad survey of paired comparisons across the whole country. A lot more depth and detail, different soils and this kind of thing really need to be looked at. But that is the start. It's a suggestion of the impact of soil health on food quality. What about a food nutrient quality soil health indicator? Here is an amino acid called ergothioneine that is produced by fungi, including mycorrhizae, a lot of mushrooms as well. It's a unique amino acid, antioxidant, anti-inflammatory compound found in the human diet. It's a longevity vitamin because it mitigates chronic diseases of aging. The primary source, soil-borne fungi, can occupy the roots of plants and then translocate this compound into the plant, going to the grain. And one of the crops that accumulates this very efficiently is oats. So oatmeal, granola bars, this kind of thing. If it's been produced under good soil health, will be a good source of this particular vitamin. But and I talked to Beelman, who's really discovered this vitamin. He says it can be extracted from soil, so can it be a relative soil health indicator? I don't know. There would be some testing. It's an idea that I'm just throwing out. Okay, I'm not going to get through all this, but there's been a lot of change in nutrient contents in different grains over the year. Here is the normal level. All these protein oils, lysine, tryptophan, methionine, are lower in corn grain that's being harvested now. Wheat, the same thing. Over the last 160 years, the last 20 years, wheat grain nutrients, zinc, copper, magnesium have fallen off in grain. But in this particular study, this is the kicker, the soil contents of these same nutrients were sufficient. So it suggests that some of our modern varieties have been more selected for abundant yields rather than nutrient quality. I think in Albrecht's day, the problem was probably the soil was depleted, but here is one of those situations where it may be some of the varieties that we're planting now. So what do? We need to educate the public, understand to eat better quality food. Kids, we need to limit their ultra-processed foods, educate them in school. I think there's some of this going on, growing food in school gardens. Local initiatives, urban gardens, like the Columbia Center for Urban Agriculture, urban farms, affordable prices, food preparation workshops, farmers markets, CSA, maybe some government policy. Here's a shot of an urban farm in Anaheim, California that they put on an abandoned military base. Corporate sponsorship, great for soil health and ecosystem services, but this is one by PepsiCo. Are they really going to have healthy foods when they're sourced? Nothing about promoting a healthy diet, but this is the kind of stuff you see. How healthy is that? But there's mixed messages sometimes. I think it's great that they're incentivizing their farmers to put in soil health practices, but let's be honest about it, what the final product is. Okay, I'm going to quit with this, okay? As I was doing this research, it was announced that the National Academy of Sciences are going to actually have a study on exploring linkages between soil health and human health. They're going to review the state of knowledge on linkage, explore potential benefits of soils, microbial resources to human health, which is a great idea. Hopefully, it will be more than just a white paper, right? Maybe there'll be some substantive coming out of this. They have a provisional committee, which I know many of these people. It's a mixture of soil microbiologists, nutritionists. You might remember Grusak gave a talk here some time ago. So I think there's some progress being made. It's almost 5 o'clock. I'm just going to stop it here. So resources. I think these will be available. And okay. Thank you for your attention. I appreciate everybody being here.